Good morning, students. Today we are going to discuss the current 4 vector and bilinear covariant, Dirac bilinears. So these two topics that we are going to discuss today, and of course we know this equation very well. And this equation is the equation of continuity, which says about the conservation of energy, conservation of probability charges. And del dot J plus 1 by C partial d by dt rho equals 0, equation of continuity. And del stands for partial d by dx, and this is your partial d by dt. So this is first order differential equation, and it is symmetry in both space and time. So under Lorentz transformation, surely this will work out. And we know that J is the current density and rho is a volume charge density. So probability is conserved. So this equation says that probability should be conserved, no other way. And current 4 vector, the title goes with current 4 vector. We know about 3 vectors in 3 dimensions, we know very well. So current goes in x direction, current goes in y direction, and current goes in z direction. We know that 3 current vectors we know already in all the 3 directions. Here we are talking about the current 4 vector, which includes time. So space and time cannot be separated. Space and time should be unified. So this theory is mainly deals with only the unification of space and time. We should not separate. Space and time should be together, and this will give you a quantity in such a way that, and this will go in space and time together. So current 4 vector means we are talking about a space, 3 currents, and 4th current. We are going to discuss the 4th current, whether really it exists or not. We are going to justify the 4th current. And we know that del dot J plus 1 by C partial d by dt rho equals 0. This is very famous equation of continuity. The current density and charge density are not separate entities in relativistic electrodynamics. So they are not separated. This is unified with a single quantity. And of course it will go into the space with grouped quantities, but we are going to say they are grouped together as J mu stands for covariant, which goes with 1, 2, 3, 4. So J mu equals J ICP. We are going to prove, we are going to justify the 4th current is IC rho. I repeat, the 4th current we are going to justify as IC rho. So we know already the time coordinate ICT, we know already. Okay, earlier we discussed about the coordinate axis, which is nothing but ICT. Similarly here we are going to talk about, and we are going to justify IC rho. So J, what is J? J is nothing but your Jx, Jy, Jz. So J1i plus J2j plus J3k is nothing but your J in all the 3 directions. So this refers the space. It refers the time coordinate together. So space and time should be together. Okay, we should not separate. It's not separate entity, it is single entity. So your J4, which is equal to IC rho, which we are going to discuss. We are going to justify, and we are going to prove that whether J4 is nothing but IC rho is a 4th component of J mu. Okay, and of course as I said, this is space part of J mu, and this will be your time part of J mu. Here the result 9.53, okay, which has been written directly, has to be justified. So we are going to justify these currents. We know about this current very well. You just take a cube of box in which charges are there, then surely we can say that current exists. If charges are moving, we can say that current exists in all the 3 directions. So this need not be justified. What of this one? So this should be justified. This comes under current 4 vector. Okay. So consider a small volume element of volume dV containing charges d rho. So we are going to have a small cube in which charges exist. Okay, the volume we are going to consider as dV, and the charge is nothing but d rho. For elementary volume dV, volume charge density rho is supposed to be constant. So rho equals dq by dV. Okay, this is volume charge density. Probably you would have studied about surface charge density earlier. are linear charge density. That is on 2 dimension, this will be 1 dimension, this will be in 3 dimension. Okay, volume charge density is given by dq by dv, we know already. So dq equals rho dv. Cross multiplying, you will have dq equals rho dv. You are going to multiply on both sides by dx mu. What is dx mu? Which is nothing but position 4 vector, which termed as position 4 vector. Of course, mu stands for 1, 2, 3, 4. First 3 goes with space, the last one time coordinate. Okay, so we are going to multiply this one by dx mu. So dx mu dq equals rho dx mu dv. We are going to multiply and divide by dt on both sides. So that will give you, we are going to multiply and dividing by equation 9.5 by dt on right hand side. Okay, so left hand side let it be like this, right hand side you are going to multiply and divide by dt. So this becomes rho dx mu by dt, and dv stands for dx dy dz. So dx dy dz dt. This equation is very important equation which we are going to discuss now. Look at this equation. So we have dx dy dz dt, and this will be 3 coordinates, and this will be your time coordinate, so 4 coordinates together. So this is 4D volume element, this is Lorentz invariant. Okay, 4 current which goes in space and time together, this is Lorentz invariant. So current vector is a Lorentz invariant. And so right hand side dx ds is 4D. Okay, now you just come here, left hand side. Left hand side goes with 4 vector. dq is charges. See how many charges are there? What we call this is dq. So it's a scalar. Scalar multiplied vector will be a vector. Okay, so this is your vector quantity. This side also is a vector quantity. So this must be your vector quantity, no other. So logic is clear. So this will be your 4D volume element, which is nothing but which is Lorentz invariant, and this is, as I said, this will be a 4 vector, 1, 2, 3, 4. So 4 vector. So this must be a 4 vector. This is your scalar, and this quantity together must be a 4 vector quantity, 4 vector entity. Okay. Now, and we know that about Lorentz transformation from one frame to another frame. Suppose we consider S frame is at rest, and S dash is moving with velocity say v, and we are going to have the charges inside the box. Just take a cubical box in which charges exist. Okay, and the charges are nothing but your dq. This will be your charge density, and that will be your volume of the cube. This box is moving with velocity v, correct? When charges move, that will constitute a current. So current density. So current density exists. I repeat, the charges which are in the box with the volume dv that moves with velocity v. So charges move, that will constitute a current density. Okay. So current density, the probability of charges together, that will give us current 4 vector. So current 4 vector which we are going to study is nothing but your J, combination of J and rho. That is nothing but your current density which is moving. Charges are there at rest. This is ordinary charges. Okay, if charges are moving, then this will become current density. So current density and the probability density together will give us current 4 vector. That's the correct definition for your current 4 vector. So now the charges are moving, which will give us the current density. Okay. So as I said, this quantity is very important. So J mu equals, we are going to consider J as J mu. So J mu equals rho dx mu by dt. I repeat, this quantity is a 4 vector. We are going to consider as J mu. So here dq is a scalar, as I said, dx mu is a 4 vector. So the product of dx mu dq will be 4 vector. Since left hand side of equation 9.56 4 vector, so right hand side must be a 4 vector, no other way. So this must be a 4 vector quantity. Okay. So as I said earlier, that we should not separate space and time. It should be unified. Okay, it should be unified as a single quantity. Okay, for 4 vector. So J mu equals rho dx mu divided by dt. For mu equals 1, we can go for first current vector. Okay, for mu equals 1, J1 equals rho dx1 by dt. For mu equals 2, this can be expressed as like this. For mu equals 3, J3 equals rho dx3 by dt. We want only J4, which is very important, which we are going to consider. So J4 equals rho dx4 by dt. We know that x4 equals ICT. Earlier we studied. Okay, ICT, time coordinate. So just substitute your for x4, that will give you ICT. You pull IC constants out, so that will give you rho IC dt by dt. dt can cancel. You have I0. So J4 is nothing but I0. So we have justified, we have proved. This is nothing but your 4 current vector. So very important thing is we should not separate space and time. It is a single quantity. Okay, it's a single quantity that describes for the current vector that moves in space-time. It's a Lorentz invariant. So J mu equals first current, second current, third one, and fourth current. So 4 current vector. It is very useful in electrodynamics. Quantum electrodynamics is very useful. That's why we are studying little bit. Okay. So J mu equals, the first one stands for J1, second one is J2, third one is J3, and the last one is J4. Okay, so this can be written as J comma IC rho. So J mu are the components of current 4 vector. The components of J in S frame can be found in S dash frame through transformation matrix. Of course, we know about this, because when you are going to transform from one coordinate system to another coordinate system, you will have to multiply by a suitable transformation matrix. So yesterday in the last class we learned about this transformation matrix, which is nothing but S we learned. Okay, only then we can transform. Okay, so you have a coordinate in one coordinate system, one inertial frame, which should be multiplied by a matrix that will give us another system, another coordinate system. The result should be the same if both the frames move with the same velocity. Okay, now we will go for the next title, which is nothing but bilinear covariant. Sometimes we call this as Dirac bilinears. Sometimes we know about gamma matrices earlier. Gamma matrices are the combination of alpha and beta. So we know already very well. Okay, alpha and beta. Alpha is connected with Pauli's pinnas, and beta is a unitary matrix. So we know very well about it. So gamma 1, gamma 2, gamma 3, gamma 4. We know very well all about 4 gamma matrices. And product of all the 4 gamma matrices will give us gamma 5. That also we know. So while studying the properties of gamma matrices, we learned all those things. So gamma 1, gamma 2, gamma 3, gamma 4, the product of all the 4 matrices will give us gamma 5. Gamma 5 also has property. It is Hermitian and all those things we know already. Now bilinear covariant, it says that the suitable combination of all the 4 gamma matrices can be found. I repeat, see, we have 4 gamma matrices. Now we are going to have the combination of all the 4 matrices. Either it can be like this. For example, we can have individual gamma matrices. Gamma 1 separately. Gamma 1, gamma 2, gamma 3, gamma 4. We can have separate. Or otherwise we can have together. Gamma 1, gamma 2, gamma 3, gamma 4. Or otherwise we can have 2 combinations. Gamma 1, gamma 2, one combination. Gamma 1, gamma 3, another combination. Gamma 1, gamma 4, another combination. Or otherwise we can have 3 combinations. Gamma 1, gamma 2, gamma 3. Gamma 2, gamma 3, gamma 1. See, something like that. Is it okay? Or otherwise we can have squares of the gamma matrices. Gamma 1 squared, gamma 2 squared, gamma 3 squared, gamma 4 squared. Now when you are going to count the permutation combinations, that will give us 16 components. So very important 1 mark question. So out of all gamma matrices, we can have 16 components. So together, okay, those 16 components may be used in particle physics as well as weak interactions. So that's why it's given as very important. Okay, so bilinear covariant we are going to discuss. It's nothing but a suitable combination of gamma matrices. Okay, and when you are going to have, suppose when you are going to take individual gamma 1 individual, then it can be a scalar. If you are going to take together gamma 1 gamma 2, it can be a tensor, it can be a vector. Gamma 1 gamma 2 gamma 3, it can be a tensor. So we are going to discuss. By forming products of gamma matrices, it is possible to construct 16 linearly independent 4 by 4 matrices. Okay, gamma is a 4 by 4 matrix, we know already. Matrices which often appear in the applications of Dirac theory, especially in electrodynamics, weak interactions it is used. We are going to express the scalar, vector and tensor in terms of solutions of Dirac equations. Gamma matrices are solutions. Okay. The following set of 6 objects comprising 16 independent components are known as Dirac bilinears. The combinations, as I said, those combinations are nothing but Dirac bilinears or bilinear covariants. Bilinear expressions of the wave functions which have the transformation properties of the tensors. All Dirac matrices are simply constants and the same value in all Lorentz frames, but when contacted with psi bar and psi. I will shortly say about psi bar. Different bilinear have their own distinct transformation properties. So these are the combinations. So we know about 4 gamma matrices, we know, and we are going to have the permutation combinations like this way. The first one, the square of the gamma matrices, gamma 1 squared, gamma 2 squared, gamma 3 squared, gamma 4 squared. The square of the gamma matrices, correct? So what will the combination? Combination will be only one. Individual gamma matrices, so this is separated. So gamma 1 is different, gamma 2 is different. So what are the combinations? We have 4 combinations. Now we are going to go with 2 gamma matrices. Gamma 1, gamma 2, 1. Gamma 1, gamma 3, another one. Gamma 1, gamma 4. Similarly, gamma 2, gamma 3. Gamma 2, gamma 4. Gamma 3, gamma 4. Any other combination, 2 combinations exist? Other than this, you just count it. That's all. So you just count it 1, 2, 3, 4, 5, 6. So 2 combinations are there. 2 gamma matrix combinations are there. When you are going for 3 gamma matrices, gamma 1, gamma 2, gamma 3, gamma 1, gamma 2, gamma 4, gamma 2, gamma 3, gamma 4, gamma 1, gamma 3, gamma 4. 1, 2, 3, 4. So 4 combinations exist. Now together, this is gamma 5. Okay, together gamma 1, gamma 2, gamma 3, gamma 4 is nothing but 1. Totally 1 plus 4 plus 6 plus 4 plus 1 will give you 16 combinations. So what we call this is Dirac bilinears. Okay. So this is the first one. First one which we see, this is the first one, which is nothing but your identity matrix. Number is only 1, which represents a scalar. Okay, it's nothing but a scalar number. And what of this one? Gamma mu. Mu stands for 1, 2, 3, 4. So they are all individuals. Okay, this is separated, this is separated. Gamma 1 is separated from gamma 2. So totally we have 4. They are all vectors. And what of this one? Gamma mu, gamma nu. The combination of 2. So we have now 6. So they are all tensors. Okay. What of this one? Gamma 1, gamma 2, gamma 3. Combination of 3 gamma matrices. So that will give us 4. What we call this is pseudo vector. I will say what is pseudo vector now. And this one will be your gamma 1, gamma 2, gamma 3, gamma 4 together. What we call this is pseudo scalar. So scalar, we know about scalar very well. So scalar merely it means a number. So we have number. Suppose we are going for under parity operation. Just think about parity operation is nothing but your mirror reflection. So you have a mirror reflection. Here one quantity exists. Okay, this quantity after the mirror reflection that will give us minus. Suppose if it is plus 4, then this will become minus 4. Minus 4 stands for pseudo scalar. So under parity operation, the sign changes. That scalar is nothing but pseudo scalar. Is it okay? Under parity operation, you have mirror image, we have a scalar. The sign of the scalar changes into this quantity. So it becomes plus 4 means it will become minus 4. What we call this as pseudo scalar. Is it okay? Now pseudo vector quantity that has both magnitude and direction. Okay, under parity operation, as in the same rule, we have a mirror image. Suppose if the vector rotates like this, then the mirror image it will go in the opposite direction. If it is in the clockwise direction, this will go in the anti-clockwise direction. Okay, it is right hand means this will be in left hand. So direction alone changes, there will be no sign change. Direction alone changes. What we call this as pseudo vector. Okay, so scalar there exists with a minus sign, pseudo scalar. Vector there exists, the direction of the change, direction changes. Okay, change of the direction, and what we call this as pseudo vector. You count it again, that will have 16 components, 16 combinations. So under parity transformation, the magnitude of the sign changes nothing but pseudo scalar. The combination of psi bar x, this is gamma n, psi of x is called bilinear covariant, and gamma n is called bilinear density. As I said, this is nothing but your adjoint spin mass. So this is your adjoint spin mass. This is ordinary one. This is adjoint spin mass. We are going to discuss only one property. The following property of gamma n can easily be verified. We know from Lorentz transformation about this. We know because in the last lecture we discussed about this. One frame to another frame, we have to multiply with a suitable transformation matrix. So suitable transformation matrix we know. Okay. So this is one frame, this is another frame. If you want to get the result, and you have to multiply with a suitable transformation matrix. So yes, psi of x. Okay, now you just take the Hermitian conjugate of this equation. We are going to take the Hermitian conjugate. So taking the Hermitian conjugate will give you dagger. Okay, and what are this S and psi? S and psi. We know that AB whole dagger equals B dagger A dagger. So yes, psi of x becomes psi dagger S dagger. So your psi dagger S dagger. Is it okay? Now multiply by gamma 4 on right hand side. So on both sides, multiplying gamma 4 on both sides, not right hand side, both sides. So we have now psi dash of x dagger gamma 4, which is equal to psi dagger of s, s dagger gamma 4. So this is wrong, not right hand side, on both sides. Is it okay? This equation. Now we know that gamma 4 square equals 1. Gamma 4 square can be written as gamma 4 gamma 4. So I am going to insert right hand side gamma 4 gamma 4. Is it okay? Previous equation is here. Okay, I am going to multiply this by 1. I am going to write this as gamma 4 squared. So I have written gamma 4 gamma 4. What of left hand side? Left hand side can be replaced with gamma, no, psi dash of x dagger, which is equal to psi bar adjoint spinor. So this can be replaced with adjoint spinor. So we can write this. Okay, now gamma 4 S dagger gamma 4 is nothing but S inverse. So we are going to replace this by S inverse. I repeat, gamma 4 S dagger gamma 4 is nothing but S inverse. It's a property. So we can write on right hand side as, instead of this we can write this as S inverse. Is it okay? So now psi dagger gamma 4 is nothing but psi bar. This is adjoint. So we can write this as like this, S inverse. This can be easily written as psi bar x, which is equal to psi bar dash x. This can be written. Okay, is it okay? Now this equation is exactly the previous one which we learned. See? So Lorentz invariant. It's very clear that Lorentz transformation can be easily done. So Lorentz invariant. Okay. So it is noted that all these covariant forms are realized in electromagnetic scattering theory, especially a set of bilinear forms are used in particle physics and theories of weak interactions. Okay. So we will start today. We will learn today about current 4 vector and bilinear covariant. Okay, Dirac bilinears we learned. Current 4 vector stands that it says that we can't separate space and time. It's a unified quantity. It's a unified quantity. So we should not separate. It's a unified quantity in such a way that the components will be grouped. The components of unified quantity will be grouped together, and we have one quantity that is nothing but a current 4 vector. Okay, and bilinear covariant, which says that the combination of all the gamma matrices can be done. Possible combinations will be 16 combinations exist, and they are used in weak interactions. Okay, bye students, we will see in the next class.